All right, well, let's go ahead and get started. So last time we talked a bit about x86 instructions, which was a recap of how all programs work at some point in time. Good work, guys. I know it's Tuesday morning and it's architecture. Everyone's excited. It's great. Especially you. No. Oh, wait. Or is that the I want it? You know, like with Caesar? Is that right? No? Okay, fine. All right, anyways, we talked about the instructions, which is how modern processors, actually everything eventually comes down to some type of instruction for a general purpose processor. We talked about the architecture in a previous lecture to that, and everyone looked at me confused, which I understand. Now that we've talked about instruction, let's go back and look at the architecture again, which is this picture up here. A quick recap, this is the little computer 64-bit data path implementation. The idea is that this architecture that I've drawn here is an architecture diagram to explain how to implement 8 basic instructions that are x86-like. So, this architecture, which you will be doing in Verilog, as an assignment, no, the other face. An assignment in Verilog will, so, what was that? Verilog assignment, you're going to be doing this. So get used to this. Also, this is not in the book, so when I assign something, you're going to be looking at the PowerPoint. Now, the book is going to have MIPS or RISC-V, depending on which book you got, and its architecture is going to be similar to this, but it's not going to be the same because this is a different architecture, the little computer 64. So the book can help you, but it's not going to give you verbatim everything that's going on.
MIPS and what was the other one?
RISC-V or RISC-V.
Gotcha.
See, is it OS X or OS 10? All right, anyways. We talked about a MUX, connects one of the inputs to the out. You have a selection bit and it selects which one goes to out. I think we went over that and people were pretty okay with that. We talked about a decoder, which does the opposite of a MUX. You have multiple lines coming in and that selects which one line coming out you wish to activate. And that's what's used for read-only memory because you select which one line you wish to activate and then we put diodes on that one line in order to signify either 1 or 0. And you need to have a 6x64 decoder, so you'll have 6 lines coming in and you'll have 64 lines coming out, and you will need to do that decoder for your assignment, so do write that one up. It's going to be a lot of copy paste, or you could look up how to generate these with a for loop. It's up to you. Just get it done. And then we'll talk about how to do a read-only memory, which is going to be a lot simpler than probably most of you all think. All right, compute building blocks. Next was the ALU, which stood for the arithmetic logic unit, and that has multiple operations or functions that it can perform on what's coming in. We talked about one was an adder, we can also do an and we can also test for equality. And the idea is that depending on what function you select coming in is what operation it's going to perform and produce the output based on that. All right, we didn't get to the full implementation of that yet, but that's okay. Sign extender, hey look, there's the Verilog code. So anyone who does the sign extender, here you go. Basically, we only have 16 bits, but our numbers are 64 bits, so we need to extend it to 64. And I said that this is the way you do it. It may not be intuitive why this works right now because we haven't talked about 2's complement, but that's okay. We will get to 2's complement possibly today. And then the register file, which is what stores the memory. If you remember from these instructions, each instruction operated on a register, so it had to read from a register and possibly write to a register as well. So R1 and R2 in the upper left are telling what registers to read from. Out1 and Out2 are the data that's stored at those registers. And then W1, W2, W1 is which register you wish to write to. Data 1 is the data you wish to write to that register. And then you have an enable bit if you want writing to happen or you don't want writing to happen. Notice also that a regular register is a little similar in that it has input and output and you just have a line coming in that enables overwrite yourself with what's coming in or not. That's standard register as well. All right, memory. We are going to just think of memory at a high level. Memory is actually a pretty complicated subject. But we're just going to think of it as a block. You have an adder and a data in, and the idea is that your reading is enabled. Notice down there you have read or write. If read is on, then you're going to read from the address and output the data at that address to data out. If writing is enabled, if write is selected and write enable is selected, then you're going to write whatever's data in to the address at adder. How are we doing? Little computer, 64-bit, based on MIPS, which stands for that thing right there, which makes no sense to you right now, and that's perfectly fine. We'll get to that. I used it for simplicity. The instruction set is based on x64 for real application, and also the move for x64 is Dr. Lin wants all their security people to know x86. Therefore, we're going to learn at least some of it in here. So when you get to his course, cybersecurity people, you will then be able to at least code in x86. Also, if you get really, really good at this, there is definitely a branch of cybersecurity that will pay you a lot of money. But we're going to use this for the programming projects. Okay, there are different type of instructions, and this is just to help us signify or group together the instructions we're working on. There's the R type where you have your opcode, register destination, register target. And the opcode here is 4 because that's what x86 uses. Notice that the opcode is, what is that, 6 bits? Yeah, 6 bits. And so that's add, and what it does is it reads from the value of register RD of the register RT, and then sums them and puts them back into RD. That's all it does. And then we have add, which does similar thing, except the operation is and. And then we have CMP, which actually stores in a separate special register that I called flag if RD is equivalent to RS. The I type, standing for immediate, the R type was register based. I type is immediate because you're going to work with an offset. The first one's called move, which is actually a load word because you're loading from memory into a register. And it's computed by taking the contents of RT, adding whatever offset is memory, reading that from memory, and putting it into your RS register, whichever one that happened to be. Store word does it the opposite direction, where the memory RS plus whatever offset you have is equivalent to whatever was in your RT RT register. So just to make sure this is clear, because sometimes this can be a little confusing, what this is doing is taking the contents of RT, let's say it's 5, add the offset, and here it could be 5 as well, so 5 plus 5 is 10, jump to memory address 10, read it, store it into RS. Down here it's doing a similar thing. It reads what's in RS, let's say it's 5, offset, we'll say it's 10 this time. So memory of 5 plus 10, which is 15, is equivalent to RT, or what was in RT. And then jump address is that if the flag, remember your flag is set previously with your CMP instruction, if that flag is true, you update the PC counter to PC plus 1 plus offset, otherwise you don't do anything. All right, back to this architecture. So the question is now, how can we implement these instructions that I provided? And those instructions I've given you, I think there's only 6 instructions so far. There's going to be 2 more just to make our lives easier, but we'll get to that in a moment. Those 6 instructions are powerful enough to basically create a Turing-complete computer which can do any type of computation. Now, I didn't say it would do it quickly, I just said it would do any type of computation. Obviously, we would want more instructions, aka multiply, in order to speed up performance, but those 6 will actually give us what we need. All right, how can we implement this? Well, let's take a look at add, and this should give us a good example. So we're going to add the contents of RD plus the contents of RS and store the result in the register RD as well. And then increment PC equals PC plus 1, so we go to the next instruction. What does that look like? Well, let's say we're adding from register 3 and register 1. Register 3, register 1, the register file outputs the data, the sum of those two. The ALU is selected to do add. We'll say 0 is add. It sends that back to this mux, which selects it, sends that to the register file as the data. Up here, it knows to forward the 3 because that's where we're writing to, and so it then knows to store the result of the contents of register 3 plus contents of register 1 back into register 3. And PC up here, we're adding 1 to it, and we're forwarding it from this mux so that this PC will go ahead and increment itself to the next program counter. How are we doing? Was it a whole lot better this time?
I mean, I'm just waking up, so.
Okay, great. That means you got it perfectly. All right. So we can design. We talked a little bit about clocks. And we use a clock in order to predictably change state or store information. One problem that we have, and we talked about the flip-flop, is that we don't know how long it would take this part to finish as well as this guy as well. And what we want is a clock to where everyone does their computation. Once everyone is done, we tell them to store the result and begin the next computation. That's the idea. Because hopefully you can kind of see that the PC+1, this circuit up here of updating the program counter, is going to take less time than reading from the register file, the ALU, and then coming back and writing to the register file. Hopefully you can see that. If not, trust me, that's the case. And if these are out of step, then the program counter might be incrementing faster than we can do the rest of the computation. So a clock is basically a gate. Start this computation, wait till this point until everyone's done. And in this example, we're adding register 3 and register 2. Notice that the change here is that the second register is now 2 instead of a 1. Actually, this is an AND because we've also flipped that to a 1. That's interesting. I wonder why that happened. Yeah, that's an AND, and then I changed it to an ADD. So let's fix that right now. Boom. So what happens when you change slides? Let's look at move. Well, we're moving. This is a move L, or known as a load word. So we're loading or moving from memory into a register. Remember, this was the immediate one, so we have an offset as well as the registers. So the idea is we're going to move into register 2 the value of whatever the contents of 1 is plus 25. So notice these are the bits for 25, which will sign extend it and forward it to our ALU, which is going to add. Here's that 0. We're going to read from register 1, and we're going to forward that as well. We don't care about this one. We don't care about this one because we don't care what it reads because we're not going to read it. And then let's see, we're going to forward 2 here, so we know that we're writing back to register 2. But notice once ALU computes the address, it goes into the data memory, which is enabled and for reading. So it reads that data value and then sends it back to this mux, which forwards it to the register file. How are we doing? Great. Good. How about the other way? Well, we're still going to compute the offset. Oh, this got a little weird. Yeah, compute the offset, forward the base plus offset to the memory, but this time we're also going to read from the other register and forward that to the data memory where we're going to enable and write to it. And that way, after computing the address, we're going to write. By the way, for each of these instructions, notice that PC has been PC+1 and we're constantly incrementing the program counter. Also notice that this opcode changes for each one. That way you can signify which line down here in order to activate each line. By the way, this means don't care. You can make it a 0 or a 1. It doesn't matter. And then compare. Well, this just compares 2 registers to an CMP flag. So 1 and 2 reads it to the ALU. The ALU has a special equality flag, and we're going to send that to another register. So I did not put the CMP flag here beforehand. I've added it just now. So this processor will have to have a little CMP flag in order to signify what the last values were for 2 registers. And then now for jump address, basically, if the flag, well, what we want to have happen is if this flag is true, we want to, did I come up? Well, I didn't update this up here either. So let's see how many of y'all have paid attention. Besides the obvious MIPS32 up there that needs to be LC64, what do we need to do? Well, we have sign extend, so we'll sign extend this up to 64 bits. But what else do we need to do to make this happen? What are we updating? Can't throw things at students, but it's so tempting. I just want like a Nerf gun or something.
I think we all sign a waiver, that's okay.
We all sign a waiver.
I think, it's never nothing.
Oh, that'd be great. Oh, that'd be great. All right, what are we updating, guys? Which register? Which one? Which register are we editing? That's right, there's a register. How many registers are there? Ooh, that's a good question. How many registers are there?
At least one.
One called register.
All right, it sounded like Perry got it. How many registers are there?
3.
What 3 registers are you thinking of?
Data memory, register file, and instruction memory.
So the memory we're not going to count as registers.
Gotcha.
The register file is a collection of, was it 32 registers? So, I mean, no, that was good.
No, okay.
So there's 32. There are more than 32 in this picture. Where are the other registers?
ALU.
The ALU is just going to be a combinational circuit. So program counter, that's another one. So that's 33, and there's one more register. Yeah, the CMP flag. Great. So, and that's what holds our state. Which one? I mean, the data memories also hold our state, but we don't consider those registers. So those registers plus the memory hold our state. What register are we updating? Which one?
Why don't we consider them?
So with data memory, they're not going to be stored as a register like a D flip-flop. They're going to be stored or worked with very differently. And there'll be a section about how memory is stored with a DRAM. SRAM does work like registers, but we think of it as memory, not as registers, just because it's a larger structure. That's all. They do function the same way, or similarly, I should say. All right, what are we doing? Yes, so which register are we updating? The program counter. What are we going to update it with?
We're adding one every time you do an operation.
Okay, sure, we're adding 1 to it, that's correct. Are we adding offset? I guess it's a trick question.
It depends.
It depends, yes. What does it depend on? The flag, right. So what are we updating? We're updating the program counter. What are we updating to? It depends on flag. So we need to somehow update this mux based on the CMP flag. So we could just forward the output from the CMD flag up to this mux to say whether we're going to update the program counter with either, notice that this one right here, if you follow it back, is just program counter plus 1. But this one over here is the sign extended of PC plus 1 plus the offset, aka this calculation down here, all the way back around to this other mux. So we could use the CMP flag to be a selector bit, but that has a problem. Does anyone see what the problem is? Well, the CMP flag's a register, so it's going to hold its value until changed. So this will work for jump address. What about for add? Does add care about the CMP flag? No. So we can't just have the CMP flag do the mux. We need to base it on the CMP flag and the opcode. So we have a giant AND, where one input is from the CMP flag. That's this red arrow right here. I don't want to draw a giant red arrow going across the whole architecture because that's going to get ugly. but it goes into this AND, as well as the opcode goes into the AND as well. So it's saying only output 1, aka select the next one, if the CMP flag was 1 and we have the same opcode, or the opcode for jump address. In this example, we said the CMP flag was 0. If it was 1, it would have selected PC plus 1 plus offset. All right, how are we doing now? Because this is this one can get a little complicated or tricky. I guess they're all complicated and tricky. Whatever. There are many more instructions, and we're going to go and discuss some of them in the future. Normally I went through a whole bunch of them right now, but we're going to pause here because y'all need to code this up in Verilog to actually understand what's going on, and we don't want to get too far down the road. Okay, what's next?